In this lecture, we shall study input-output in Haskell. Till now, the view we have taken is that a program is a bunch of functions. A function of type A arrow B produces a result of type B on an input of type A. The programs are run in GHCI by invoking a function on some arguments. GHCI automatically displays the result on the screen provided the result can be shown, or in other words, provided the result is a type that belongs to the type class show. But this is a limited form of interaction with the user. We would like a slightly better user interaction model like in other programming languages. So the questions we have are, can we execute programs outside GHCI? How do we let the programs interact with users? That is, accept user inputs midway through a program execution, print output and diagnostics on a screen or to a file. Can interaction with the outside world be achieved without violating the spirit of Haskell? So these are some of the questions that we consider in this lecture. We shall first consider standalone programs. Execution of a Haskell program starts with the function main. This is not something we have seen till now. Till now a program was just a bunch of functions and GHCI automatically interpreted any function that we entered in it. But if you have to write a standalone program, execution has to start at some place, and that is the function main. Every standalone Haskell program should have a main function. Here is an example program. In fact, this is the simplest compilable program that we can write. Main equals put str, which stands for put string, hello world, with a new line character here. So this, as the name suggests, puts a string on the screen. So the way we run this is to save this into a file named hw.hs, hw standing for hello world. We compile this file using the command ghc hw.hs. Compiling this generates the following files: hw.hi, hw.o and hw. The file of interest to us is hw without any extension. If you see this on a Unix terminal, you will see that the permissions for these two are read write, but hw has execute permissions, or in other words 755. We can run the executable using ./hw. Dot denotes the current directory. ./hw means that the executable file hw can be found in the current directory. If you add the path where your Haskell executables reside to your path environment, you can just invoke the function using hw. But for now, in the examples, we'll just use ./program name. GHC is the Glasgow Haskell compiler. GHCI that we have been using till now is the interactive version of the compiler. One can view GHCI as an interpreter or a playground in which to test your programs. If the program is intended for use by others, then it's usually written as a standalone program, compiled using GHC and shipped. Compiled versions of programs run much faster and use much less memory as compared to running them in GHCI. You can check the various options that GHC offers by typing ghc --help in the terminal. You can use ghc --show options to know all the options that you can provide, all the compiler options that you can provide to GHC, but this is a huge list. If you want to know more about GHC and GHCI, you can consult the GHC manual at this URL, which is part of the official Haskell page. So we have learned how to write a simple program which stands alone and runs on its own, compile it and run it. Let's study the program in more detail. Main equals put string hello world with a new line character at the end. Put string is a function. The behavior is that put string str, put string of string, prints the string str on screen. So clearly put string is of type string arrow b for some b, because the input is a string. But you notice that in this main program, the return value is not used at all. So perhaps we can say that put string doesn't return anything of significance. The type null or empty, as it is called, denotes nothing, or it can be used to model nothing. This type empty is denoted like an empty tuple, and it consists of a single value, which is also denoted by an empty tuple. So the question is the type of put str string arrow empty? But we notice that put string is not an expression that returns a value. And moreover, it has a side effect, which is that of printing something on screen. So how do we account for the side effect? So if you actually type :t put str in GHCA, you will see that GHCA says what the type of put str is. The type is string arrow IO empty. If you check what the type of put str hello world is, you will see that the type is IO empty. So what is this IO? IO is a type constructor, just like some other type constructors we have encountered in previous lectures, like list or B tree or AVL tree, etc. So therefore IOA is a type whenever A is a type. But there is a distinction. Recall that the value constructors and internal structure of user defined data types like list, B tree, etc. are visible. But the internal structure and constructors of IO are not visible to the user. In other words, the user cannot do any kind of pattern matching based on the constructors of IO. One way to understand IO is as follows. Its declaration can be thought of as data IOA equals IO. The IO on the left is the type constructor, the IO on the right is the value constructor, and the values are of type real world arrow, the pair real world comma A. Real world here is not an actual Haskell type, but it's just one way we can understand what IO means. Assume that there is a type which represents all states of the real world. So we can think of IO as taking as input the current state of the real world and producing a new state of the real world due to side effects, and also producing a value of type A. In other words, object of IOA constitute both a value of type A and a side effect, namely the change in state of the world. Technically, an object of type IOA is not usually referred to as a function but as an IO action. This is an important distinction. An IO action produces a side effect when its value is extracted. Any function that produces a side effect will have return type IOA. So let's get back to put string. Put str is of type string arrow IO empty. Put string takes a string as argument and returns the empty tuple. And in the process of producing the empty tuple as output, it also produces a side effect when the return value is extracted. The side effect in the case of put string is that of printing on screen the string that is provided as argument. Main, as you can see, is of type IO empty. Main is always of type IOA for some A. Now we talked about side effects in the course of executing an action. What kind of side effects can happen? Examples are printing on screen, reading a user input from the terminal, opening or closing a file, changing a directory, writing into a file, etc. Or maybe launching a missile, driving a truck, etc. Now there is a close variant of put_str, namely put_str_ln. You can read it as put string line. Put string hello world prints the string on the screen, whereas put string line hello world prints the string and appends a new line on the screen. So put string line str is equivalent to put string of str plus plus the new line character. Standalone actions are not of much use unless you can perform a lot of actions, and Haskell provides a way to chain actions. We use the command do to chain multiple actions. For example, you could say main equals do put string line hello, put string line what's your name. Do makes the actions take effect in sequential order, one after the other, in the order presented in the text, in the program text. Here the indentation is important in the do command, but since the indentation is sometimes hard to keep track of, Haskell offers an alternative, friendlier syntax, which is to use braces and semicolons. Main equals do open brace put string line hello, put a semicolon, put string line what's your name with a semicolon, and close the brace. And these actions can also occur inside let, where, etc., etc. For instance, main equals do act 1 semicolon act 2, where act 1 is put string hello, act 2 is put string line world. So you can define local actions. Here are some more actions. Print, whose signature is show a, implies a arrow IO empty. This outputs a value of any printable type to the standard output, which is the screen, and adds a new line. Put car is a function from car to IO empty. It writes the car argument that is provided to it on the screen. Get line is of type IO string. It reads a line from the standard input and returns it as a string. The side effect of get line is the consumption of a line of input rather than the production of a line of input. And the return value of get line is a string. Get car is a function that reads the next character from the standard input. We saw that getLine is of type IO string, but is there a way to use the value that is returned by getLine? In other words, we need to bind the return value of getLine to an object of type string and perhaps you would use it elsewhere. Haskell provides the following syntax for binding, and the syntax is reminiscent of assignment in some other languages, which is just to say less than hyphen. It's like a left arrow. For instance, you could do this: main equals do put string line, please type your name, n bound by getLine, or in other words, the output of getLine is bound to n, and then you can use it here in the following action, which is put string line hello plus plus n. This has the effect of first asking the user for a name, waiting for the user to input her name and press the enter key, and then printing hello followed by her name on the screen. Please note that this is wrong. Put string line of hello plus plus get line. This is because plus plus is a so-called pure Haskell function or operator, and its arguments are list A and list A, and the output is list A. The arguments are not of type IOA. Therefore, you cannot use getLine in the context of a plus plus. You should always bind it to some name and then use that name here. GetLine is not a string, it is an action that returns string that has to be extracted before the use, and the extraction is the binding that is mentioned here. At this point, we need to look a little closer at the distinction between functions and actions. A function that takes an integer as argument and returns an integer as a result has type int arrow int. An action that has a side effect in addition to consuming an integer and producing an integer has type int arrow io int. This distinction that Haskell maintains is in contrast to languages like C or Java, where the type signature of both functions that have side effects and functions that do not have side effects are just int arrow int. And in general, any function is assumed to potentially produce a side effect. Any function can produce a side effect. There is nothing in the language itself that prevents functions from producing side effects. Haskell enforces this distinction between pure functions and actions. The functions that you have seen till now that are free of side effects are called pure functions. Their type gives all the information we need about them. Invoking a function on the same arguments always yields the same result. And the order of evaluation of the subcomputations does not matter. Haskell utilizes this to great effect in applying its lazy strategy. In contrast to functions, actions usually have side effects, and Haskell maintains this distinction by designating their output types with an IO. The presence of an IO in the type indicates that actions potentially have side effects. External state is usually changed, and the order of computation is important, as in actions inside a do command. The actions take place in a sequence. So, sequencing is something that is inherent to actions. Moreover, performing the same action on the same arguments twice might have different results. For instance, consider the following action: greet user, which is of type string arrow io empty. Greet user greeting equals do. Inside the do block, we have put string line, please enter your name. Name, which binds the value of getLine. The return value of getLine is bound to name. And then we put another string on the screen, put string line, hi, plus plus name, plus plus, a full stop, plus plus greeting. So this greeting is something provided as an input. In main, we can do the following: greet user welcome, greet user welcome. You see that the greet user function is being called with the exact same argument twice, but the two actions might print different things on the screen depending on the name that is input by the user at this point, because the greet user action itself has a way to get input from the user and type the input back to the user, namely the user's name. So this shows that performing the same action on the same arguments twice might have different results, and this is a fundamental difference between actions and functions. One can combine pure functions and actions, but in a limited manner. We can use pure functions as subroutines in IO actions, but not the other way around. The Haskell type system allows us to combine pure functions and actions in a safe manner. No mechanism exists to execute an action inside a pure function, even though pure functions can be used as subroutines inside actions. I/O is performed by an action only if it is executed from within another action, and main is where all the action begins. So main embeds some actions inside it, and each of those actions might be a do block with further actions inside. Let's look at a few examples. Here is one example, which is to read a line and print it out as many times as the length of the string that is input in the first line. Here is the program. Main equals do get a line and bind it to INP, which stands for input. It's a variable of it's a value of type string. Call the function print often to print input length input times. If input is of length n, then print often n input will be called and it will be printed n times. That's achieved as follows. Print often is a function from int and string to IO empty. Print often one string is just put string line string. Print often n string is a recursive function. Inside a do block, you first put string line string and then you print often n minus 1 times string. This is an example of a non-trivial interaction with the user. But what if the user inputs the empty string? Notice that if length of input equals 0, there is no case here that catches it. What if the user inputs the empty string? To handle this, we need to define print often 0 string. Recall that the return value of print often is IO empty. For print often 0 string, there shouldn't be anything printed on the screen. So can we just define it to be empty? But the output type then would be empty and not IO empty. So we would get a type mismatch. This means that we need a way to promote the empty tuple to an object of type IO empty. This is precisely achieved by the return function. The return function or the return action takes v, which is a value of type A, and produces an action of type IOA. If v is a value of type A, return v is of type IOA. With this, we can fix the earlier example as follows. Main equals do get a line and bind it to input, print often length input. The crucial case is this: print often 0 string equals return empty. This matches the type properly and it also handles this case, the case of not printing anything on the screen. Notice that here there is no side effect as such, but still we designate this as type IO empty. So this illustrates the fact that if an object is of type IOA, it need not necessarily produce a side effect. It only indicates the potential to produce a side effect. Whereas a pure function which is not, whose type is not embellished to the IO, can never produce a side effect. Here is another example, n times, which takes an integer and an action and repeats the action n times. This is a generalization of what we did in the previous example, where we printed input out to the screen some n times, where n is the length of the input. So n times 0a is just return empty, n times na is do a followed by n times n minus 1, n times n minus 1 a, which is to do the action a n minus 1 times. Now we can read and print 100 lines as follows. Main equals n times 100 act, where act equals this block. which reads an input from the user and prints out that input. Get line, bind it to input, put string line input. This action is repeated 100 times by main. Strings are not the only things that can be read. We can read other values, but these other values have to belong to a type A that is an instance of the type class read. For this, we use the function readLine, which is denoted readLn, whose type is readA implies IOA. All the basic types int, bool, char, etc. are instances of read. Therefore, you can use readLine to read integers, booleans, characters, etc. The basic type constructors also preserve readability. So, for instance, list int, the triple int, char, bool, etc. are also instances of read. Here is the syntax to read an integer. Input readln : IO int and bind the result to input. So since readln is supposed to cater the reading of any of these types that belong to the class read, you need to specify which type you want the input to be. So here is an example. In this example, we read a list of integers, one on each line, and finally terminated by -1 into a list and print the list. Main equals do ls is read list. Ls is the return value of read list empty list. So read list is a function. We are providing the empty list as an input to read list. It is of type listInt arrow IO listInt. So it produces some side effects, and its return value is a list of integers, which is what is bound to ls here. And then it so happens that read list reads the list in reverse order. So we show the reverse of ls and invoke put string line on it. In this way, we read a bunch of integers, one on each line, and output them as a list. Here is the description of read list. Read list L equals do read line as an integer. This you denote by saying readln : IO int, bind the return value to input. If input is -1, then there is nothing more to do. So you just return L, which is the list that was provided as input. Else, you have read the input, you add the input to the list by saying input : L, you add it to the head of the list, and you proceed with the read list function, presumably reading more input. In summary, Haskell has a clean separation of pure functions and actions with side effects. Actions are used to interact with the real world and perform input-output. Main is an action where the computation begins. GHC can be used to compile and run programs. There is a lot more to explore in I/O, but only the most basic material is covered here, which suffices for rudimentary interaction with users.